Sorry about the cut. Had to free up some space on the memory drive. So the sort of experiment, not a practical experiment you're going to do, but the results of an experiment that you use to show the extra stability of benzene is by looking at the enthalpy changes of reactions. So if we measure the enthalpy change of hydrogenating cyclohexene to form cyclohexane, that has a delta H of minus 120 kilojoules per mole. So it is by no means an easy reaction to do, and there's a high activation energy, but it is exothermic. It does release energy. Now, if we went to hydrogenate cyclohexa 1,3-diene, so cyclohexa 1,3-diene with 2 equivalents of hydrogen, so we're hydrogenating it twice, again to form cyclohexane. Don't think I've got the number written down. Oh no, I do. No, I don't. We'd expect the delta H though to be approximately twice as much of that, because we're doing the same process twice on 2 double bonds, and I don't think it comes to exactly this, but it is approximately minus 240 kilojoules per mole. So a very, very simple a simple consideration of this, you predict minus 240. It's probably slightly less than that. It will be slightly less. It's probably about 230, but it's pretty close to the predicted value of just doubling it. However, if we take benzene, that's very much not what we see. So you can hydrogenate it. So with 3 hydrogens to form cyclohexane, that is the reaction is far less exothermic than predicted. So the prediction, if it were just followed, if it was the Kekulé structure, so if it was cyclohexa 1,3,5-triene plus 3H2, we would expect a delta H of minus 360. So this is very much a prediction, but by applying the principles from this first one and this one, and that again, I'm making up that number, it's the true answer is pretty close to it. What we actually find with benzene though is the delta H comes out as minus 208 kilojoules per mole. So we have an extra stability. Of 360 minus 208, which gives us 152 kilojoules per mole of extra stability. So that's quite a substantial. That's a pretty substantial difference in energy, just due to the delocalized ring of electrons. So extra stability due to the delocalized So that goes. So that's a calculation that you are highly likely to need to do in your exams. It's quite a common question. There's multiple examples of it on the database of questions. So quite a popular one. Make sure you know how to do that calculation. Now we have to take a look at a new reaction mechanism. If I'm not mistaken, this is the last reaction mechanism that you will come across. So there's more reactions where you're going to take some other reaction mechanisms and look at them in more difficult contexts, but actually this is the last mechanism. It shows actually how much we've managed to do since lockdown, really, and that is electrophilic substitution. It's an electrophilic substitution reaction. Now we need incredibly powerful electrophiles in order to react with benzene, as benzene is very unreactive, and for the reasons we discussed in this previous thing here. So we've got that extra 152 kilojoules of stability due to that delocalized aromatic ring. So electrophiles that react with alkenes that we saw all the way back at the start of year 12, or at least start of organic, they're not reactive enough to react with the benzene ring. We need to add catalysts in there to make them much more reactive. Now there's two main reactions that fall under the mechanism of electrolytic substitution that we're going to look at. The first is called Friedel-Crafts acylation, and the other one is the nitration of benzene. So we're going to look at those two reactions. So we'll first take a look at, I think we'll do the nitration of benzene first. So we'll look at the nitration of benzene. Now, the reagents we need for nitrating benzene, we obviously need benzene. We need basically pure sulfuric acid, or very concentrated, and very concentrated nitric acid as well, HNO3. Now, the actual chemical species that's going to react with benzene is not present on here. There is a reaction between the nitric acid and the sulfuric acid that takes place before the benzene gets involved. So we're going to form a highly reactive intermediate due to H2SO4 and HNO3 reacting with each other. Now, sulfuric acid is a very strong acid. It is a stronger acid than nitric acid. Nitric acid is a very strong acid, but less so than sulfuric acid. And so we're going to, what takes place, I'm going to go into a tiny little bit more detail than you actually need for A-level, and then I'll show you how you can simplify it for the A-level questions. And what's first going to take place is an acid-base reaction between the sulfuric acid and the nitric acid, where the nitric acid is going to act as the base. It's nothing you've ever come across before. You think nitric acid is an acid, it's got the name acid in its name. It's a less powerful acid than the sulfuric acid, so it's going to be forced to act as a base. So the H2SO4 and the nitric acid. Sorry, NO4, NO3. Now, acids, they are proton donors. Bases, they are proton acceptors. The sulfuric acid is going to donate an H+ or a proton to the nitric acid, and the nitric acid is going to act as a base and accept that proton. We're going to go HSO4 minus plus H2, so it's gained that extra hydrogen, that extra H plus, NO3 plus. So we've had an acid-base reaction, but our acid has donated an extra hydrogen to our base to form H2NO3 positive and HSO4 minus. Now HSO4 minus is perfectly stable. The HNO3 plus though is not very stable at all, and it undergoes a decomposition. It's going to break down into different products. So the H2NO3 positive, that breaks down into a water molecule, and an NO2 plus. I think it's called the nitronium ion, I might be wrong. Now this is our reactive intermediate. This is our species that will actually react with benzene. This is a ridiculously powerful electrophile, but we need a really powerful electrophile to actually react with benzene, because we have to break that highly stable aromatic ring in order to get benzene to react. Now what you'll need to do though is write an overall equation for the production of the reactive intermediate. Now to do this, you need to we can sort of cancel anything that appears when we combine these two equations together. So I'm going to add the left hand sides together and add the right hand sides together, and then cancel anything that appears on both sides of the equation. So if I add the left hand sides together, we've got H2SO4 plus H2NO3 positive plus HNO3, and on the right hand side we've got water, NO2 positive, HSO4 minus, and H2NO3 positive. And if you look, the H2NO3 appears on both sides. It's an intermediate in the production of our intermediates that then reacts with benzene, which is a bit confusing. But because this appears on both sides, we can cancel it, leaving us with our reaction being H2SO4 plus HNO3, H2O plus NO2 plus HSO4 minus. Sorry, it's not all in one line. Now, you'll sometimes see a different version of the overall equation that is taking this a tiny little bit further and just thinking about that water that's produced in the reaction. Now, the water is a reasonably good base. It can accept a proton fairly easily, and it can react with another equivalent of H2SO4. This can act as an acid again, donating an H plus to the H2O, and so you sometimes see a second version where we've included as an extra H2SO4